Okay, good morning, everybody, and good afternoon also for our Chinese friends. And welcome to this new edition of PAU, the Programmable Audio Workshop. My name is Yann Orlaret. I'm the Scientific Director of gllm, a national center for music creation based in Lyon in France. gllm is an institution which is dedicated to the contemporary music creation, where artists, musicians, and composer works together in close cooperation with researchers, particularly in the field of computer music. Among the various software that we developed here at gllm are the low latency server Jack 2, the dynamic music score system InScore, and the Faust programming language. All these projects are all open source. Some few words about PAU. The goal of PAU is to bring together designers of programmable audio hardware and designers of tools and programming language together. The day is organized in the form of 6 workshops. These workshops are quite concrete and technical, and they are all based on the theme of this year, which is modular audio synthesis and programming. And this is a very interesting concept, not only because there is this revival of modular synthesis, but also because this is a very wide range concept that interests architecture, music, mathematics, computer science, and engineering also. And if you look at the first version of the ENIAC computer in the late 40s, it really looks like a gigantic Moog synthesizer, and the concept of programming by patching modules is not only of musical interest, is of interest for many kinds of programming. So this is why we're so happy to have this theme this year. So the first talk will be by Max Brucker. Max is an electronic musician, computer music designer, and sound engineer. He writes music and software for contemporary music and live performance, in particular for dance. On stage, he uses software such as Max or Reactor associated with homemade instruments, modular synthesizer, and various sensors to elaborate his idea. And he teaches also signal processing and sound design at university and art school. And he collaborates with gllm since many years. And in his talk, he will explore various conditions of interacting, playing, and composing with this kind of approach. So Max, it's to you.
Hello, everyone. Nice to see you all on this channel. I'm really honored to be presenting this, opening this PAU session for 220. As Jan said, it's been a concern for me to try and find some interactive systems, because I'm pretty sure that most of you who use computer music softwares and video softwares, not only, but also hardware stuff, are always in this kind of situation where they have to change protocols to send any information from one place to the other. So this is a kind of hassle. It's always been. So my main question was, what kind of protocol is the easiest one? So these past years, we all know MIDI as a protocol, because this is one of the most famous ones since the 80s. And the MIDI system is really one of the most reliable ones because all of you know that the MIDI is something that is written in the hardcore of all your OS computers, your OSs of all your computers. And along the years, MIDI has changed, and one of the most famous ones now is called MPE for a multi-channel and complex MIDI system, which I won't be talking about because I don't have any of those to show you right now. I would have if lockdown in France had, cut us from the studio, so I'm at home. So I won't be showing you any hardware system neither, even though I have a Eurorack system, which is really nice. So I will be talking about Eurorack systems, but particularly in VCV rack. So coming back to the protocols, one of the major problems that I had along these years is trying to send information between one software like VCV rack, another software like MaxMSP, or it could be Pure Data, Ableton Live, because Ableton Live, which is a really very famous DAW now, but I use it mainly because you can write your max patches and put them inside Ableton Live. Well, there are some issues there, but still, let's not talk about that part. And I wanted to talk about also video, because I'm going to show you how to interact with the video system too. So the first thing first, I'm going to show you, for those who are not familiar with VCV rack, let me show you, present a screen, and let me show you this first. So you should be seeing shortly the main page by VCV rack. So VCV rack is, as it says on the main page, is a Eurorack simulator. So what is Eurorack? It's actually modules that have functions, just like in programming, general programming, but this is older than computer programming. This is where MaxMSP probably got its first ideas from. And VCV rack is sort of an emulation of all types of modules. The nice thing about it is that it's open source. There's a very big community of people working on it. And it's actually easily hackable and easily usable to produce music and video. You'll see some people doing that too. So first thing to do is probably to install VCV rack and create an account. So I'm already logged in. And well, Rack doesn't have all the modules that I'm going to show you. So you will need to install a library, some libraries, in fact, that you can find in the library section. There's a library here. You can have a look at that. And so the first thing that I will be using is a library by Trowasoft. So Trowasoft is a really nice library using OSC, Open Sound Control, that was supposed by many people said that Open Sound Control was supposed to be the new MIDI. So it's a network protocol to send information from one place to the other. Well, in my humble opinion, OSC never achieved that properly because OSC, it's not dead yet, but it's a bit complicated to use. It's not as intuitive as MIDI would be, though MIDI also has its hassle. MPE, which is the MIDI extension now, especially since Ableton is going to implement MPE within its software. MaxMSP has also done that. It's going to be probably one of the next steps in controlling your softwares. Well, Trowasoft implemented OSC within VCV rack. So you will need to install this library. Then the other one is one of my favorites is Audible Instruments. Those who use Eurorack are actually probably familiar with Mutable Instruments. It's the open source part and probably the most intelligent, to my sense, Eurorack system ever made, because Émilie Gillet has been developing these modules in hardware, all open source and open hardware. So you will find all over the world different types of different variations of her modules, and this is the software application and software fork of it. So I will be using it, and there's this very nice library by Bog Audio with tons and tons and tons of modules, and they're really intelligent. And this is probably the best way to go into synthesis, because it relies on very old school definitions of stochastic synthesis. So, and the last library will be Plateau, and Plateau, like a plateau in French, is another library, and there's one really nice reverb that all the VCV Rack fans use, is the Plateau Valley, and this one is, it's a plate reverb, but it really sounds nice. So let's go on. Let me show you VCV Rack. So this is VCV Rack. This is the first patch that I'm going to show. VCV Rack actually is very simple environments where you have a blank page with a few modules, but you can put your own modules inside, the ones you had in your library. So once you've installed your library, take a look on the internet for that part, because this is very well documented. You can put them by right-clicking in your window and just clicking on the library you want. So in this patch, I will be sharing all of this. I installed the TrowaSoft and some native VCV Rack objects. And of course, the audio part. So I'll have to explain that later, but I'm going to show you Ableton Live, so you can see my voice right here. And I created groups for the 3 examples that I'll be showing. And this is a track from VCV Rack. So what I'm doing right now is I'm going to send data through OSC, and this data through OSC comes from MaxMSP, will come and arrive inside VCV Rack that would produce a sound, and this will be sent to Ableton Live via audio. So I have to find workarounds for that, and it's a bit of a complication, because the OSC part, as I said, you see, is quite simple. It's just a module you install, and if you're familiar with OSC, you can easily send that through Pure Data or Max. It doesn't matter, or another OSC compatible software, and have VCV Rack produce music. So the other part, the tricky part, is sending the audio from VCV Rack to Ableton Live or your other piece of software. VCV Rack has developed a system to an internal virtual driver that you could use, but is actually deprecated. They chose not to continue developing it because there are other proposals, other pieces of software that are really nice too on your various platforms. I think the best one ever is Lovely Jack. There's a very famous one called Soundflower that is, historically speaking, it comes from Cycling, and Cycling has developed that for a long time easily. So this is the one I'll be using. There is another one called Black Hole, and Rogue Amoeba has developed another one called Loopback. I think that none of those is really satisfying, but I'm still going to use that because the problem we have right now is that Jack is no longer supported on Mac systems. This is probably because of Apple's change in policy, because of in their software policy. This is an ongoing question. It has been an ongoing question for years now. So what I'm doing is I'm just going to send audio from VCV Rack to Ableton Live. But the main issue that I'm having is that I want to send audio from VCV Rack to Ableton Live and back from Ableton Live to VCV Rack. And this is not possible right now. You had to find several workarounds. Just a quick a quick note about that. I've tried for this demonstration to aggregate different sound cards. I have a physical sound card, my Fireface, and a Soundflower running at the same time. I try to aggregate both, but VCV Rack keeps on crashing. I have, buffer underruns, some drills and sounds that will get stuck. So using that between Max and Ableton Live, same thing in Reactor. Loopback only instantiates 2 outputs from your software. You cannot have multi-channel outputs. I didn't find a proper solution for that. And Black Hole only has 16 channels. I actually need more. And Soundflower seems to be the best solution because you can have 64 channels at the same time. So this is probably the best way to go. If you wanted to send, 24 channels from one software to the other, Soundflower will be the most reliable. There is one piece of software called Dante Via, where you can aggregate some pieces of hardware with the Dante protocol, which was developed by Odinate. But still, that isn't really satisfying, and VCV Rack crashes. So let's stick to that. So first example I'm going to show is a Max patch. I'm going to show this to you. And in this Max patch, it's a pretty simple Max patch. And I've used some objects that are native to Max that are called beep. And so let's unlock this. And the beep modules you can find in your in Max are actually Eurorack or Eurorack patches. They simulate Eurorack patches. So I'm going to use one of those. It's called Poisson. It's a random generator, a random pulse generator, and 2 LFOs and a lag. So the LFOs here are modulating one another, and the lag is smoothing the signal. All of this is turned through this into OSC, into data, which is bad. That's actually really bad, but that's the best way I found. And all of this is sent to VCV Rack. So the main concern I had is what happens with, is there any jitter between one software and the other? How do I clock them? Because this is when you work with softwares, you often have to think of, how am I going to clock my softwares, especially when you're working with rhythm. When you have a rhythmic proposal and rhythmic music, you need to have something steady. So here in this patch, I'm using Poisson as a clock. It's triggering every 3 seconds. And so let's listen to this. It's this click. So here you hear Max just clicking. And let's see how it works here in VCV Rack. So the TroaSoft module, you need to activate. As you can see, no connection. So let's hit the config button and enable configuration. And I'm receiving in the port 7000 and receiving port 7001 and out to the port 7000. This is the OSC IP. So once I've enabled it, you can see in my scope that there are parameters, something is modulating here, and you can see clicks. This is my click from Max. So now let's listen to the click here. There we go. You can hear a click. So every time Max is clicking, it's arriving here. And I'm going to use this tick, the small trigger here, and I'm going to split this signal to hit a resonator, very famous resonator by Audible Instruments, Mutable Instruments. It's a model resonator, nothing you couldn't achieve with Faust. So this Stefan is going to talk about that, but there are many ways of making a model resonator. The most famous is this one. I'm using a quantisympathetic string model, and I've also doubled it with an FM operator that has its own VCA in an envelope. So every time the trigger arrives, it is split and goes to my resonator, and then it's also triggered once in a while. It also triggers once in a while the FM operator. To achieve that, I use a Bernoulli gate, and Bernoulli gate is just this is named by Mutable. It's just a It's just a deterministic system where you have 50% chances to have a signal coming in and out. So when I have a trigger coming in. When your pot here is in the middle, you have 50% chances that it comes out on the left side or on the right side. Here, I want it to be more on the left side. And this is going to my gate input, triggering my FM op. So let's listen to that. So you can hear two things. First, a trigger coming in, something that is, hit. It's strumming my model, and something is modulated. This is the other part. The modulation coming from Max here in OSC is actually modulating this parameter structure. It's a bit tricky because it changes according to the model you're using. This is specific to mutable instruments. But here what is happening is the content change. So let's do the FM up here in a while, trigger once in a while. There you heard it. Of course, I tuned in. So one thing, this is just a very simple patch where everything is triggered every 3 seconds. Now I'm going to introduce some chaos to make it more randomatic. And I've also patched the other Bernoulli gate module to the freeze parameter of my plateau reverb. Now let's listen to that. So every time the trigger arrives, there's a probability that it freezes, hence long tails in the sound. Oh, very long tails. Well, the music it produces is really, dramatic, sort of cinematic music. There's a reason for that, and I didn't start the introduction by that, but this is something you should know. Well, I think it's implicit, but when you use a piece of software or whatever module you're using, it implicitly implies some type of music. There is no such thing as a piece of software that it would achieve everything. Even Max has its own way of thinking, hence its own music implied with it. So every time I use an operator like FM op or a plateau reverb, the way it sounds is, some sort of cinematic way. And the thing is I will produce are always kind of dramatically cinematic, if I may say. It's a little difficult to produce pop music with that. You could, if you had a different definition of mine in pop music. So let's stop this patch. I can hear my reverb is frozen. If I don't unfreeze it, it will continue. One of the nice things about VCV rack in this case is that what I'm doing here, I could reproduce that with my Euro rack. because the objects I have here, I have them in my Eurorack too. The thing with Eurorack, and this is one of the main debates around Eurorack or synthesizers, is that if you wanted to start Eurorack, it's a fair amount of money to invest. I mean, every module is expensive. You couldn't have 100 oscillators just like that. You could achieve that very easily with at least rack, or if you know how to patch and you know how to program, you could do that with FOSTA without any difficulty. But still, there's one thing really nice about having a physical synthesizers is that you can play. There's the ongoing debate about whether using a synthesizer is better than using a piece of software. Well, I use both of them when I produce music, but when I play with an instrument, it stays an instrument. And instruments are, something that propose music on their own. So once you've built your own synthesizer, well, obviously it's going to narrow down the type of music you can do, of course, but it also helps you produce something. When you write a piece of software, you could do anything, but you have to choose all the time. And so I think it just lacks of creativity. So this is, well, it's my opinion. This is why I have both systems working together. To get rid of all the driver problems with the Eurorack system, I invested, and there are different kind of systems, I invested in the Expert Sleepers modules, and Expert Sleepers actually are physical modules that convert ADAT or USB audio stream into CV gate, making it compatible with your Eurorack modules or your other type of modules. It could be Bushla, it could be Mu systems, but these are really interesting. So it really opens the way you can work with your environment. Let's go on. So I'm going to turn off this first thing and open another one, the second VCV program. So as you can see, there are modules I already used, and this one is a bit different. So what I did here, I created 3 times the same thing. So let's have a look first at, at this. So I have the MIDI CV module resonator again, using a different model. It's a model resonator this time. Another module called segment generator, also by Audible Instruments. So I need to explain what these do. So MIDI CV is a MIDI to control voltage converter inside VCV rack. It receives any MIDI incoming MIDI, and when turning it into volt per octave, gate, or other parameters, velocity after touch, PWM, W, clock, etc., etc. But the nice thing about that is that I'm using the internal MIDI bus inside your Mac, your Apple systems. You have an internal MIDI bus called IAC bus. You could easily achieve a virtual MIDI bus with any piece of software. If you use a Max patch, it will automatically create a virtual bus. You can see it here from Max 1 and 2. If you're not using Max, you could use another piece of software like MIDI Yoke or MIDI Pipe. There are numerous softwares that could help you create virtual buses, and they're all free and open source. So as you can see, I also have Millimin running, who also creates its own MIDI bus. So it's fairly easy to have a virtual MIDI bus between your softwares. What I'm doing here is I made this patch, this Max patch. Well, I didn't entirely make it. I actually forked an idea. I made this Euclidean sequencer. So Euclidean sequencer, you probably need to have a look on that on the internet for those who are not familiar with the Euclidean sequencers. But What I made here is a polyphonic Euclidean sequencer. This is a very traditional sequencer you'd find in Eurorack systems. Many developers have made those from make noise to 2HP to there are numerous sequencers you can find in the Eurorack world. So this one is actually a fork by Derek, who is a programmer, a French programmer who made a sequencer called Zeuclide. So I forked it into a polyphonic 10-track sequencer you can find here. I will also give this freely to everyone because it's all open source. This polyphonic sequencer, let me explain how it works. Every track here will generate a note according to a division. This division, called steps, can go up to 64 steps. So from 6 steps to 64. Let's say I will divide it in 45 steps, have 14 divisions, and I'll ask him to make equal divisions in these 45 steps. And there you go. On so every slider here represents an event. This event is, every time this gray thing is going to hit the slider, it will generate the note G3, or another note that you would determine. The height determines the velocity. And I implemented this, a MIDI bus, a virtual MIDI bus, so every track can send to a different destination. So this is kind of handy. You can also shift the position of your event to come. The other thing I implemented, you can see it here. Let me close this window. This part called map is, for those who use Ableton Live, is a mapping system, obviously, but it's going to map the parameters of your sliders to whatever parameter you choose. So here I chose to map the channels 7 and 8 to L time is actually the delay time of a delay plugin. And 8 is going to this parameter here, sends B. It's the amount of auxiliary send that is going to the echo. So I'm going to automatize and the amount of info I'm sending to the delay. So let's have a look again at the sequencer. I'm going to recall the presets. There we go. And sorry, a small cut in sound. Okay. There we go. So every time Euclidean sends a track, these 3 tracks, they will arrive here in these MIDI channels in Ableton Live, and they will be sent to my 3 instances here in Rack. So let's listen to that. Let's close this, open the track, and hit play. So here you see the first one has 32 steps, the second one has 32, but the third one has 34 steps. This is why they're not in sync. So the models I'm using here, the model resonator, are tuned to sound a little bit more like bells or metal pieces that are struck. And let's change the presets. Wow, that was a dramatic end. This thing you just heard, I made it for dance. Obviously, you can hear a pulse. There's something rhythmic about that, but it's off. It's really off. Well, that's polyrhythm. It's polyrhythmic stuff. Most of you are familiar with that. There are numerous ways to achieve that, but if you had to write that, I mean, write a score with that, this one is really simplistic, but if I had to show you the complete evolution of it, it's a bit complicated to write. So the nice thing about Euclidean sequencers is that you can write really complex stuff. Sending the MIDI to one place, we could of course sample all the MIDI that is sent by Euclidean and put that in a score, and then just reproduce that with the real live instruments. So this is how we did it for a dance piece I did years ago. And having this complex structures also always evolving with a steady pulse, you can feel the beat, but you can't predict the way it's going to fall. So that's the really interesting part. And the automation is a really nice one. The thing I also implemented and changed that from the original patch by Derek from Euclid is that you can here choose to edit your preset. You can choose your presets to be changed by MIDI. You can shift register every note, and you can listen to incoming MIDI. What does this mean? The preset here, every time I send a MIDI note, let's see that in Ableton. I'm not sure everyone can see that properly. Every time it receives C-2, it will change to preset 1. This will change to preset 2. This one will change, D-2 will change to preset 3, etc., so on and so forth. So you can dynamically change the routing. So I made an off one that initializes everything, meaning that you can write a score like that. I don't know why for this presentation it's clicking, because it's probably because of the audio stream, but in real life it doesn't. So let's listen to that again. Second one. I think you get the idea. So let's stop this. There we go. Let's turn this off. Okay. So Resonator, this module, you can see it here. I have 3 of those. In real life, that would cost a lot of money. So if you wanted to work with multiple model resonators, VCV rack or another system like a FOST and a max patch or a PD patch would be the way to go, because in real life, having every module costs 150 or 200 euros, depending on the way it's built. And today we'll see that there are probably cheaper ways to achieve that. So if you wanted to go polyphonic, you would probably use VCV rack. Nice thing about that is that the polyphony system is already implemented inside VCV rack. Have a look at that. There's a Facebook page that documents that very, very, very well. So let's have a look now at the third example. No, I don't want to save. So here we go again with the same modules. Oops. So in this patch, I am using again a max patch to generate OSC. I'm using 2 resonators again and plateau as a reverb. But what I try to achieve here is a more complex system where interaction goes from one software, Max goes to VCV rack. VCV rack makes the audio part, and the audio part is streamed to Ableton Live just as a mixer. And so you're receiving this through the audio channel. But this part is the interesting one. This thing called Aeolian, dBiz. dBiz is a sequencer, is an XY sequencer. So this is a traditional sequencer you would find in your rack modules. Every time a trigger comes in here, it will shift and play the note on the left. Every time it comes here, it will shift the note and play on the right. And this one, it will shift and play the note that's upwards, and this one, it will shift and play the note that's downwards. So we don't know which one of these 4 is going to receive a signal. So first things first, let's turn on the configuration, enable OSC. Now it's receiving, it's ready to go. Let's open the max patch corresponding to that. Close this one, and there we go. What I did here is I actually programmed a system that will detect an amplitude. Every time an amplitude is reached, it will trigger something and then randomly distribute to the 4 outputs that go to VCV rack. So I didn't really program this thing. I forked this onset detection that you can find in your package manager under the US Upshot library. It's a really handy library. It's all Max MSP, so it will patch, but it's really handy for that. So I'm using here a drum loop, this famous drum loop that all Max users know. Let's listen to that, if it's all open. There you go. Everyone knows this one. Let's turn it off, turn down the volume. And let's have a look what is happening here in rack every time it sends something. I'm going to turn the volume off so you can see that Max is banging every time it reaches an amplitude, a threshold. And there it goes. You can see that the yellow button is changing from one pot to the other. Now, what if I wanted this to be in sync with some video? Nice thing about OSC is that I can send that to Millumine too. Millumine is a software that generates video. So here you can see I have found some images on the internet, and it shifts every time, not every time. I'll explain why. It shifts in sync when there's a bang coming. And now let's listen to the audio part. So as you can hear, let's turn this off. You hear it's always the same notes. Why is it? Because it's always shifting inside this reservoir of notes that are tuned to according to a certain scale. And this is the interesting part, where every threshold is just going to choose randomly inside a reservoir, hence making some melodic things. Now, this is also a thing I used in dance, where you need to have a certain melodic structure. You don't need to, but we chose to. So let's have a look at the max patch again. Turn off the drum loop. What if I used a pulse generator again? This is the other part. And I'm going to use the pulse generator again, but this time I'm going to hook up 4 of those. And this pulse generator, oh, by the way, this pulse generator isn't Max stuff. It actually comes from SoundHack, and the developer who developed that in the Beep library, if you have a look at the help file, he gives every information. It's just a basic random and chaotic piece of program he did on SoundHack. So SoundHack, sorry, Super Collider. It's Super Collider stuff ported to Max. I think it's even Gen. So this Poisson thing, pulse generator, is I turned off the chaos, and I looped the output of to 3 other instances of Poisson. This means that this is the master clock, and the 3 others are actually tuned to be subdivisions in time. I'm still doing polyphonic polyrhythm here. So let's have a look at that and change to my pulse generator system. So you can see it flashing here. And let's listen to that. Like a illumine. Well, if we're here that I use that trigger audio and video, it's kind of related to a sound. You could, of course, put an input here and have the onset detection detects incoming signal from an instrument, and then make it generate sound inside VCV rack and go to Millimin at the same time. This is how when I would set up my system. Set up a system to have a complex audio and video stream at the same time. Could write a piece out of that. But what I did here with a steady pulse sounds a bit like minimalistic music, I'd say. Minimalistic music like some Reich or music, but there's no repetition inside. The only thing that is repeated is the harmonic scale. So let's continue. So I'm turning off the pulse. As I said, you can have a microphone coming in. What if this microphone was my voice? Let's see if it works. I have an input here, and I've hooked it up to my onset detection. So now it should be triggering. Is it? Yes, it's working. And you can lower the detection. As you can see, every time my voice reaches the threshold, it will trigger a note here and an image. The images are not always triggered. There's a reason for that. This object here is a shift register. You can find a sequential switch, sorry. You will find that in VCV rack. It actually switches the inputs to the output. So if there's no sound, if there's no input, then there's silence. This is a way to avoid a continuous stream of audio running all the time. This is one of the major issues you would have with synthesizers turned on. They keep on generating sound. So this is my way of creating silence. There are others, but this one is nice. And there we go. So this is probably I'd say the neatest way I found to hook up some complex systems between different softwares would be OSC, even though I still believe that OSC has its own issues and it's not the best way to work. What I'm really missing now is a real programmable patch bay, something that you would choose between different softwares. Say I have a software that has 16 outputs, another that has 4, and have them all being merged inside a piece of software, but I could choose to split them, merge them, and send them to other softwares. This would be really nice and convenient. This is what Jack does in a way, but because Jack can't add signals together. It can only split them. But what would be nice is sort of mixer, patch bay. In the Eurorack world, we would call that a unity mixer or a multiplier. Basically, these are just the systems that we would use. But right now, there is no steady way to make that. I'm not sure if you guys or guys and girls have a way to achieve that. I found several workarounds, but they don't seem to fit the purposes we're needing. The MIDI system is really going to be here for a long time, as I said, particularly since Ableton has implemented that inside Live 11, and this piece of DAW is a very famous one, so lots of people use it. I'm not sure it's a good thing, but things are going to change accordingly. These past 15 years, lots of things have changed in the audio domain. So why not dream of a huge control voltage, let's not call that control voltage, but audio stream that we could reroute wherever we wanted to. As we said, it's easily mappable to a piece of hardware like Expert Sleepers or another piece of hardware. You could easily turn that into a control for external gear. The tricky part about that is it's always a one-to-one signal when you send CV. So, but it makes it easier to understand. So I would go CV all the way if I could inside my softwares as well. So I think I'm a bit in advance with the timing. I don't know if Jan is back there. Probably. Mm. Mm. Yeah. Well, I must admit that most of the time it's when you program your things, you try to make something that you know very well, because there's one thing on stage is a certain situation, and producing music for others or for yourself to make a tape music is completely different. So on stage, why is it different? Because there's an audience. When there's an audience, you always lose your concentration. I mean, 90% of my concentration just vanishes. So I need to have a piece of software and gear that I know well. This is why it's interesting to have a synthesizers, because I can rely on it. I know what's happening here. I make very little mistakes with it. As if I was programming, I can do lots of mistakes. And let's say that the huge amounts of possibilities. Yeah, as you probably saw when I right-clicked on VCV Rack, I have like thousands of modules. How can I choose? I have to experiment with them. So it's a complete different thing. Doing things live, you need to rely on something you know, and because your goal is not to explore, your goal is to make music live for people. So sometimes it's interesting, but the nice thing about Eurorack, I mean an instrument, is a hazard. I mean, chance that something new can occur and you can react to it. And you know how to react with it. If you do that with the software, if you're experimenting, sometimes it goes wild and you don't know how to get out of it. You're just stuck with it and you need to figure a way. Sometimes it crashes also. That's hopefully for this demonstration, nothing crashed, but I had numerous crashes trying to build up this presentation, and even having the audio stream go to you guys with 4 different softwares running at the same time. I can tell you my CPU is really peaking right now. It's so this means I can't, with a brand new MacBook, I can't really rely on it. So nice thing is having another piece of instrument working on that side, producing music. I would get rid of VC Rack and do that with my Euro Rack. That will sort of clear my mind and be really assured that I have something running, you know, because for you guys who are familiar with the Max MSP world and programming, as I've been doing this for the past 20 years now, we've had so many crashes live with the audience that is not, I mean, that is, we can't do that anymore. It's done. We have to stop that. That is not music. We have to find a way to be sure that something musical is producing. What I mean, that's my opinion. I do music for people, and I do music. I don't do research. Research is one part when you work, but at a certain point, you need to have a steady and solid programming stuff so you can present it. Even though it's still experimental, sometimes you have pieces 90% experimental stuff and crashes. I had, unfortunately, numerous experiences with that. And you always have the feeling of it's a failure in a way. I'm not sure if I'm clear for that, but I'm so the protocols here, I sort of, I think everything relies on that, because the software, you know them, but the way you communicate with them is the tricky part, and this is the part that crashes all the time. Not to mention if you had a huge stream of OSC running from sensors to your patches, it almost always overloads your machine. This is a very famous thing. So you need to narrow this down. It's a very refined thing to find, I think. I see that. We have to switch to Rust to avoid part of the crashes, says Stefan. Yes, we do. The funny thing I have to share with you guys, because for this presentation, I was thinking of showing you something I've been trying to work on. I'm not the only one, but I generated with Euclidean, as you saw, some notes that are sent to VCV Rack. What I did is I recorded the notes, the control voltages, frequencies, and the gates. I recorded them into an audio, a buffer. And this audio buffer, I just use that and try to use that as a new control source. I've put that in one of my modules called Morphogene, and the Morphogene, I try to use that to remote other pieces of my modules. The thing is that with the 1 volt per octave convention in the Eurorack world, we have a problem. It doesn't the audio isn't, you know, it will clip when you're trying to use control voltage for pitch. What happens is that the pitch, when it reaches the volts above 1, it will clip. But you need 5 volts to control the pitch. I'm not sure if I'm clear right now. The other guys are probably better on that part than me. But so I tried that on a cassette player. I recorded control voltage and gates on an analog cassette player. And that is so much fun because you can, let's say you record a loop with a sequence, have it turn it around. What if you could slow this down and you could make it faster or slower? You would, of course, everything would detune and you would slow down the speed of your sequence. And this is what I did. And it's so much fun to do. I tried to do that with the Morphogene, but in the digital world, it doesn't work at all. You had to oversample everything. I'm not sure if I'm clear, but
so apparently I'm not here on the YouTube stream. Sorry for that. There are some question marks for you on the. Okay.
Have you found ways to get VCV rack out of software and into hardware with something like an Arduino Raspberry Pi? Oh, that's a very interesting. So I haven't found pieces. I haven't found solutions for that. But if you continue, if you keep on, Brandon, if you keep on looking at the stream to the day, I think I don't know when we'll see that afterwards. Sorry, just. There we go. Afterwards, we're going to see that on a Teensy, if I'm correct, right? So Teensy is probably a solution. On a Raspberry Pi, that would be kind of easy because you could, you know, easily make a PD patch, a pure data patch, and yeah, Roland is going to speak about the Teensy world, so he's going to probably show you how to program that on an even simpler piece of hardware. But with the Raspberry Pi, you could do that with pure data. The other tricky part you would have to need to have a proper ADDA converter, and I'm not sure the Raspberry Pi is really good with that thing. I don't have much experience with that. I think recent audio interfaces let you use audio outputs as CV outputs. Not all of them, unfortunately. Most audio outputs actually filter out CV because control voltage is bad for a sound engineer. As a sound engineer, I can tell you that. We usually filter that out because it just blows your PA. It's very dangerous stuff. It's continuous signal is the worst thing you can have. And a lot of modules exist as hardware modules, of course. Yeah, that's right. Roland will speak about that. I mean, he's the guy for that question. No, the reason I use expert sleepers is pretty simple. Actually, I have to be honest with you guys. Most of the time when I go on a gig, I have my Fireface 802 hooked up to an ADAT system. And the secondary ports of the ADATs on the Fireface, because there are 2 inputs and 2 outputs, secondary port is used for the modular. So the ADAT is completely DC compatible. So I have my module that's completely integrated with absolutely no delay between Max MSP, Ableton Live, or whatever I'm using, and the mixer for the PAs. So this is why I'm using expert sleepers, and their converters are really good quality converters because I also use them as input and output not only for control but also for sound. If I have a microphone running in my modular, I could, you know, send that to my computer without using my Fireface. So it's really handy for that part, though it's kind of expensive, though.
Okay, so thank you very much, Max. I don't know if we can applaud you, but I can try.
Thanks, guys.
And And so the next talk will be by Making Sound Machines, which is a duo of artists and makers from Düsseldorf. Making Sound Machine is composed by Enrika Giesel and Roland Nebe, and they build kits, modules, and do-it-yourself projects as well as their own circuitry, and use the project that they build to make music. Enrika studied audio engineering in Düsseldorf and holds a master's degree in electronic engineering. She develops music hardware as a day job and tinkers with her own designs by night. And Roland is an artist, musician, and composer also from Düsseldorf with an academic background as a classical performer and media producer, working with Auska, Volker Bertelmann. He has contributed to numerous motion picture soundtracks, including the Academy Award nominated score for Lion. Together with Andreas Huck, he runs Warp Type, a group of graphic moving image makers creating live visual and producing artistic video content for symphonic orchestra, classical ensemble, and composers all over Europe. And they will talk about and guide us through building a simple prototype polysynth with Faust DSP, Arduino, Teensy 4.0, and modular. So, Enrika and Roland, it's up to you.
Hey, hello.
Hey, good morning.
So yeah, first of all, good morning to all of you. We have the croissant ready. We have the coffee ready. The first question of all would be, can you hear us? If anybody could just quickly type that in chat that it works.
Ah, nice.
Okay, thumbs up here. And the other thing, maybe Enrika, you can play a note on the hardware real quick.
Yeah.
Are you hearing that as well? All right, thumbs
Perfect.
up all around. So everybody watching this after the fact, this was a live stream. Everything that happens. You know how it is. And this is also, of course, part of the programmable audio workshop 2020 holiday. And yeah. What is this all about? We are, first of all, we're Roland and Enrika. We got introduced already. We're a couple of makers and making kits and DIY projects, and also making our own hardware. And we're using some of them as what building today. And so some people videos with Faust running on a Teensy 4.0, Teensy 4.0, and yeah, we're running Faust on it. We have a Teensy 4 that receives MIDI via USB. The Teensy runs Faust code, producing the audio. We have a computer that sends MIDI via USB, and that acts as a relay, basically. And the MIDI that we play comes from a simple MIDI controller. Let me play you one of the videos real quick so you know how it sounds in a more musical context.
We don't hear sound, I guess.
Ah, wir hören.
The sound of the instrument is not working for us.
Yeah, we are checking. Ist das mute? Ist die Quelle mute?
Okay. Yeah, I'm sorry about that. We're just gonna skip the video part for now. I think it's on our YouTube channel if you want to hear it with sound. Sorry. let's go to the cam instead, and maybe you can play some chords on it. Yeah, so this is all generated on the Teensy, and it's all made in Faust code. So it's a very simple polyphonic synthesizer, but it's already yeah, just something that spawns in code and runs on hardware. So and I think the big idea here is I think everybody that wants to do something in hardware in the end has to tackle like 3 problems. They need to be a musician, of course, to have the musical idea what they want to do. They need to be a software coder, so they can write the program, and they also need some skills in putting together the hardware. And so each of these things has become a lot easier in this combination. And while we know that this is not a finished thing in the end or a finished module in the end, it's a really, really good start to get into it. So let us walk you through what you need to actually build it. And we're starting, of course, with the Teensy 4.0. And yeah, we have one in hand right here. It's a really small microcontroller dev board with a really fast CPU, so you can, or MCU, you can run it at 1 gigahertz, I think. No, at 1 megahertz. So it's really, yeah, it's really a fast core. Then the next thing you need is the Teensy Audio Shield. So that's a small board that has the codec on it, and it runs basically what it does. The Teensy generates the digital audio, and then the codec translates that to an actual audio output. And this is one of the things we talked about before. So this is a really good converter, and you can get good audio quality out of it. So you need that board. So the next part you need are stacking headers. Let me zoom in on these again. Here they are. And can you show real quick how they go into the board?
Yeah, so we have a basic way of putting together a sandwich. We have the headers like this, and then we can put this into a breadboard, as you can see here. Yes.
Okay, so the next thing you need is basically the same thing, but with pin headers on top and on the bottom.
Yeah, and we put them in the Teensy like this, solder them on, of course, from the other side, and then can we can have every pin outbreaked as well to put in some potentiometers or sensors or other stuff.
All right, so the next thing we'll need are jumper wires like that. So basically those connect on top of the pin headers. So you can, the pin headers you don't need for connecting the audio shield, you can use for other stuff like reading inputs and outputs. Yeah, there's some handy ways to do that as well, which we're going to show. Maybe just stack up that thing real quick, and let's have a look at how that's will work. Yeah, so there's the audio shield. in between goes the Teensy. And then attach like those jumper wires on top.
Yeah, they basically go on top. Or break out the left and right channels from the audio shield.
Yeah, you actually need to solder this, of course. We would workshop, but and we've like the whole thing ready.
And for breaking out the left hand, here are some where you can put all your and make with jumper wires.
Yeah, so the audio shield either comes with the headphone output, which is not so practical for your director dealing with. So in the end, need the same. So we would always just break out the actual those, and for this you basically pins slotted together, and you can get them in the variety basically. And a really cool thing though that we want to show you, this is a mutant project as well, and she built these mutable breadboard friends, and the breadboard friends are little circuits that slot breadboards.
Yeah, you can see it plugged in over here already. Here we have one not plugged in, and it holds 4 jacks to and yeah, tip and switch of those jacks are available via these pins, and so it's very handy to plug in a jumper cable to connect.
Yeah. So instead of building the circuit on a breadboard, you would just plug in this pre-made PCB with 4 jacks already on it. Or there's other variants as well that have potentiometers. That just has 4 ports and a lot of jumpers. Every you build with pin header, you can just plug in, and we kind of really like this idea, and we started building our own sort of sub circuits with that. For example, these are filters where you would just go and connect to the pin header, and then you would go have basically a test ready on a PC to the image. So you can prototype really rapidly.
Like Legos.
Yeah, hang on. So I want to show. Of course, these connectors, Donkey Kong. We just wanted to, because they're they're basically the connectors to hook up the patch cables, and they have a switch. So a really cool thing is that you can unhook. You can unhook your circuit if no cable is connected. So you can get rid of a lot of ground harm that way, just because of unpatching the inputs physically in circuit when no cable is attached. That will be really convoluted explaining that, but great. You can get that with a great DIY store. And so the last obvious part here is, of course, a MIDI controller. We're using today an Akai MPK Mini. which is one of the cheap ones, but that has already everything you would need. It has node inputs. It has controller CCs, and it has some pads to play notes. And so this already has a lot for little money.
And the nice thing is it has eight jacks. Sorry, 8 knobs. So you get like 8 parameters you can control.
Yeah, basically, and that also brings us already to one thing that's really, really different in hardware as opposed to software, is whatever you do, you will run out of knobs, right? I mean, you will have 8 knobs that control 8 parameters, and you have to find a way to sort of deal with that. And so in the like these MIDI controllers, really nice because they constantly remind you of, oh, if that parameter is not so important, maybe leave it out, or maybe lump it in with another parameter and make them interconnected. So we're going to talk about that later. And so the other one we wanted to talk about real quick, so this is a little higher end, but the cool thing about that is it doesn't only have it's a Arturia Keystep Pro, and this one doesn't only have MIDI, but also control voltage outputs. So that lets you hook into the modular world a lot quicker, because you won't only get the MIDI output, but you will also get voltage outputs, and done in a quite intuitive way and still comparable to sequencers that are in the Eurorack. It's still comparatively cheap. I mean, like Eurorack sequencers can get complex real quick and are produced in really small numbers, and then they start to get really expensive.
Yeah.
So this might be if you want to splurge, this is a nice one. And so yeah, the next thing we want to talk
software.
Yeah, the software and how the architecture, basically, how are we building it?
Yes. So do we want to first show the software bits, or?
No, just...
Okay, yeah. So how are we building it? So basically the heart is built in Faust. There we are building a simple oscillator, which we will show later how we build it. And in Arduino, we are then using multiples of this one oscillator for the polyphony. And also we are reading pitch and gate from the MIDI controller and setting envelopes for the Faust oscillator, like ADSR, with our MIDI CC commands. And then we are mixing all those oscillators together to one stereo output. And that is done by the Teensy audio library. Yeah, so that was like the software part. And in hardware, we are using MIDI. The MIDI is generated with our little keyboard, and we are hooking it up to a PC. And also we are hooking up our Teensy as a MIDI device to a PC. And at the moment we are using MIDI OX for patching it together. But you could basically also use a DAW or some other MIDI loop program, basically.
Yeah. So again, if you play some notes.
Yes. So I don't know if you can see it. This is the MIDI OX on the screen. Okay, I don't think we can see it. Okay.
Yeah, but what you can see there is that the MIDI notes are relayed via the computer. And yes. So the Teensy actually offers you pins on the underside to make it a USB host as well. And that would probably be the next step that you wanted to take, to just make it a USB host. But then on the other side, it's really, really nice to have the computer to have a quick look whether the messages you're sending are actually the messages you wanted to send, and it's a nice control step between. And honestly, for the whole development part, you have the computer there anyways. But of course, there are a lot of steps you could then take to make it more of a standalone thing. So and basically making it a MIDI host, making the Teensy a MIDI host would be one of those things. If you don't want to go that route, you could also go ahead and make a hardware MIDI connector that uses the UART port. And the code for that would be quite similar as to what we show right now. So one really quick thing, we published all the code. So if you want to follow along after the fact, hang on a real quick.
Yeah, you can see the GitHub link.
You could go to our GitHub. It's github.com making sound machines, and the repository is the only one in there at the moment. It's Faust on Teensy. And we made 2 directories. One is additive synth _Faust. This contains the DSP code. And we went, we went through it and commented in a lot of things. So if you have any questions about how that works, it's in there, and we're going to explain it, of course, as well. And then we have the Teensy code, which is already the generated code from Faust thrown in with the Arduino code. So this, if you install the stuff that we're going to talk about later, will hopefully just compile and upload to the Teensy Arduino. And yeah, I mean, GitHub, if you don't know it, you can just download the code as a zip from here. And so the very first thing we would show you is how the Faust DSP code that's sitting here will look in the Faust IDE. And so, yeah, I mean, I guess most of you know this one. This is the online version of the Faust IDE, and it's available at faustide.gram.fr. And because we noticed that in previous talks, it was really, really hard to actually see the code, we put that code on slides for you. So, but first things first, here's what we're trying to achieve. We're building in Faust, we're building a really simple voice. So this will become one voice in our polyphonic patch in Arduino. So as you can see, it's parallel processing 8 different partial harmonics, but this is going to be one voice. So we're going to have this 8 times in the end. And the Teensy will in the end run 8x8 of these harmonics, so 64 harmonics. Yeah, this is something we pulled from the Bela examples. So there's not that many examples for Teensy, but the Bela examples are really, really nice. And if you take our code and substitute the Faust code for some of the other examples, you will be able to run really nice stuff on the Teensy as well. Of course, there are some memory constraints. The Bela is based on the Beagle board and it has a lot more power, but it's also a lot more expensive. So I think it's a great trade-off. Faust IDE I showed you already. That sits at faustide.gram.fr. And it's really, really nice. You can run the code in your browser and just see.
Yeah, you can see beforehand if it breaks or if it makes the sound you imagined to make. So that's very nice.
Yeah, so that's really cool. And what you need to do is you need to paste the DSP code into the window there, and then give it a name. We call it Faust additive.dsp, and you just have to keep in mind that the name you put in there, you want to name this nicely, because you're going to need it later if you want to integrate it into Arduino then. Yeah, so the first thing here is the Faust code oscillator.
Yes. So
yeah, so the thing is here, we lowered the resolution of the sine oscillator in order to make the computation easier on the Teensy MCU. So for that, you use read table, and then you basically just reduce the table size by 1 bit. Yeah, that actually makes the code a lot slimmer. And as we're running, yeah, like we said, as we're running a lot of sine waves there, this is a good compromise to just deal with it with more efficiency. Then the next thing here is setting up a user interface for gate, frequency, and gain. And one thing to note right here is that, okay, so you have the blue variables. They are the variables you use inside Faust. And you have the orange variables. These are the variables you will going to see later in Arduino. So it's your choice if you call them the same or call them differently. We figured out for us it's easier to call them the same thing, because you don't get confused what you're actually doing. And yeah, so just remember, blue variables are inside Faust, and the names of the user interface objects, which are in orange, that's what you're actually talking to in Arduino then. The other thing you can see here is that you set the default values here. For example, for the frequency, the default value is 440. And then you set the limits of the frequencies, so which the lower limit is 20 hertz and the upper limit is 20K. And you just have to keep them in mind, because of course in Arduino you could set things outside those limits, and then you might run into troubles of just stuff not behaving the way you wanted. We didn't have any bad crashes, but you're just going to have stuff like nodes ringing too long, or I don't know, frequencies clipping at the top range or something like that.
yeah, or the knob has a strange range.
Yeah. So just keep that in mind. You're setting the limits of your DSP code already here, like the nominal limits you want to achieve. So the next thing we implemented here is a filter, and I know that is uncommon for additive synthesis because you don't usually do that. But we figured out that it's really, really fun to play, and it makes it can carve out the harmonic resonances really, really well. Maybe you want to.
Yeah, and also we using a resonant low pass, and the resonances are very fun to play with. So
yeah, maybe you want to play a couple of notes. And if you sweep through the macro. Yeah, you almost get like Formanty type sounds out of that, and I think that's also a nice point about making hardware modules apart from the theory that's behind the instruments. you also have to find stuff that's fun to tweak and fun to play in the end. So, and that gives you a little bit more freedom and opportunity to carve out the sound. So then the next piece of code here is the harmonic oscillator. And this is really interesting part of code because it uses an iterator range that is triggered later with par. Par does parallel processing. I can show you that in the main function in the end. And so what range does, it just creates instances of the user interface for the ADSR for each of the partials. So we're going to create 8 partials. Each of the 8 partials has the ADSR in the end. You will get a user interface for the volume for each of the partials. And in the Faust UI, they're represented as sliders. So if you hit run in the Faust IDE, you can already play with those. Arduino doesn't care if you have a slider or a number entry or whichever of the user interface types. So you can just choose the one that you like best for that here. And the other thing that's interesting here is that the parameters are smoothed. So you don't get steppy response from your knob inputs in the end. So then at the end of this code is the process part, and this is where the whole code comes together. You parse with parallel. You parse through 8 instances of the harmonic oscillator. You combine them all together. And then you run them through the resonant low-pass filter, and that's basically our patch here. So again, here's which parameters we will have in the end in Arduino. We will have the gate, frequency, and gain, and they set the fundamental pitch of the harmonic oscillators, while all the other partials are whole number dividers, no, whole number multipliers, so times 2, times 3, times 4, and so on. We will get the gate, the note on or off. We will get the gain, which is the overall volume. We will get the filter frequency and filter quality. We will then get the filter makeup gain, which is just something you can play with to counter like peaks and also the drop off in perceived volume. And then the fun part here is with the with this percent range iterator. Faust makes you a user interface for all 8 instances starting with 0. You get volume 0, volume 1, volume 2, and so on up to volume 7. And these are for one instance of the generator. These are, the individual volumes per sine wave, basically. So here's where you can really play with the harmonic oscillator. And you can also get the same thing for the ADSR. So you can set each of these ADSRs per sine wave separately. So just note that in the end, we will also have to set for 64 sine waves, we will also have to set 64 parameters. So you will see in the Arduino code, just to keep things easy to read, there's a lot of granny coding where like blocks of code are duplicated and copy pasted just to image or just to mirror that you're setting the 7 parameters here and done. I think that sometimes help if you look at it. And then, of course, last step you will need to do in Faust is you need to export the code. And for that, you get the make sure you have selected your project here, the correct DSP, and then you hit the little truck, and the export should be set to Teensy and Teensy as architecture. If you hit compile, you will get the download button. And once you downloaded everything, you will get the binary.zip, which actually doesn't contain a binary, but contains a text file C++ and the header file for that. And these two you drop in the same location as you would set up your Arduino project, which is, if you look at the GitHub, that's what we already did for you here.
Yeah, it's the same folder. So we have a folder named like your Arduino sketch. Then you have the .eno, and in there you also have the C++ and header file.
Yeah, so these actually just go into the folder, which is really cool. So that's really great integration, and it's really quick. And so where are we here? So now we're basically done with the Faust part.
And next we would show how to set up all the parameters in Arduino.
Yeah, so first things first, what you need is you need to install the Arduino IDE. It lives at arduino.cc. It's a simple install. Then you need to install the Teensy libraries. Those you can get at Paul Stoffrigen's website. That's the guy who makes the Teensys and designs them, and also offers a lot of code. So it's a really nice site. Sift through there, see what you can find in terms of libraries that are already pre-made for Teensy. It's great stuff and really well prepared, and good examples too. And then there's one special thing that you need to do. You need to go to the Arduino folder, your Arduino install, and you need to change the linker for Teensy 3.6, 4.0, and if you have one, 4.1, from GCC to G++, just in order to for the Faust thing to compile and link into the project correctly. And there's a much better explanation for that at this URL at faustdoc.gram.fr. And there's tutorials about the Teensy, and then there's this special note about the Teensy 3.6. Let me show you that real quick. The page looks like that. And there's a description what you need to change in order for that to compile. And I know this has been a little stumbling block for just people trying this out, so make sure you do that. Otherwise, your code won't compile. And so the first thing we would look at here is the overview, basically, of what we're trying to achieve. This is not really code, but this is basically a quick, dirty overview of what we need to do in the code, so just that you know what we're talking about next. So the first bit is we want to import the audio shield, and we want to import the code from Faust. We want to then create 8 instances of the Faust harmonic oscillator, and we want to group them together, n and n plus 4, so voices 0 plus 4, 1 plus 5, 2 plus 6, and 3 plus 7 make up one voice. And that's so we get this nice detuned analogish sound. Do you want to play a couple of notes?
Yes.
So there you can hear you have this nice chorusy thing, and that's because we use two 2 harmonic oscillators per voice, basically, and they're slightly detuned like they would be on an analog synthesizer, and so you get a much less static sound. And that's a theme you will also hear throughout this talk, that we try to sort of break up a little bit the stability of the sound by detuning things, and also giving a little bit of leeway to the parameters. And there are already easy ways to do that. Then what we want to do is audio library stuff. So this hooks into Paul's code. We want to use the Faust harmonic oscillators and route them to the individual left and right channels. I'll show you in a second how that works. We will want to set up MIDI to note frequency conversion, or MIDI note to frequency conversion, which what that means is, I'll also show you later. And we want to set up the polyphony. And then comes the setup loop in that, or setup function in that we want to just set the mixer gains, enable the audio shield, define the handles for the USB MIDI callbacks. So this is really good functionality, because in the loop, then you just say you want to read the USB MIDI. And what that does is the loop is basically free, or and the audio processing is done the whole time, but inputs are only processed if a MIDI note comes in. So what you want to do there is catch the incoming events, and then you got the handles, the MIDI note on, MIDI note off, and control change. These take the 3 variables that MIDI provides you with: the channel, the note, and the velocity. And you catch gate on or gate off there. You catch the pitch, and you want to handle the voice allocation there, just so that you don't run into problems with how many notes are pressed, and if somebody's pressing the same note over and over again. And so you need a bit of code for that. And then the most interesting thing are the control changes. We have 8 CCs here, and we set 1 to the volume of the fundamental, and there's a nice trick to that as well. We set the next CC. We do a macro. We set the volume C0 to 7. In CC3 and CC4, we do the center frequency filter, and the 7, the sustain, and 8, the release of the ADSR. So let's just look at the code real quick, how that works. You include the audio library. You include Faust additive.h. This is the header file from the Faust export. Then you instantiate just the I2S and the chip itself that's on the audio shield. So that's code that just gets those 2 running. And then comes the interesting part about the Faust integration. What you do here is you make 8 instances of Faust additive, and Faust additive again is the DSP code that we got from Faust, and you just give them variable names. So we just call them additive synth 0, 1, 2, 3, 4, 5, 6, 7. And again, what we want to do in the architecture is combine 0 and 4, 1 and 5, 2 and 6, and 3 and 7. So here is the mixer stuff. This one really cool thing is you can actually go to a graphic user interface tool at Paul Stoffagen's site, It's pjrc.com/teensy/GUI. And there you can generate basically this sort of patch for you. And this is already very familiar for people who are into modular synthesis. What you do is you create mixer objects, and then you hook up the ins and the outs. And I've pasted a little screenshot here. Basically, we mix the additive synth 0 to 3 together in a mixer of 4, then 4 to 7 in a mixer, and then we need to recombine them. So the Teensy mixers always have 4 inputs and 1 output. So what we are doing here is once for the left channel and once for the right channel, we're combining the inputs and sending them to the left and the right channel. And yeah, I mean, this is a bit tedious stuff in the code in the end, and it's a lot longer here. So whenever you see the dots in our pasted graphic here, just know that there's a lot more of the same code basically there. But the gist is make mixers, make patch codes that connect a mixer in and a mixer out, and then it results in the signal flow that you see on the right here. So the next thing that is set up here is the node number to frequency. It's an array that just tells all the 127 MIDI node numbers which frequency actually corresponds to which node number. And it's the, yeah, I don't know, it's node number 0, C0 is 8.18 hertz. That's how you read that. We commented the node names above that, so you can actually check for accuracy. You can add decimal points if you want it more accurate. And so here's the first real neat trick. We make a function to set the ADSR. And so we have control over each ADSR for each of the harmonics, which is really, really cool. And so that does mean we don't need to set them the same value, right? So what we do here is we get the value that's going to be the 127 from the CC. And then we do some math here, which is explained on top. But what we want to do is convert it to a floating point value between 0 and 1. And what we then do is add a scalar, just a multiplier to some of the values. So what happens here is for the fundamental, the attack is the longest. So the fundamental needs to, the fundamental comes in the slowest fashion, and then the highest harmonic comes in really quickly. Maybe you can again play single notes. So what you can hear here is that you can actually get a timbre change just over the attack, which is really, really cool. So that makes it lively again. We do the same thing for the decay, just the other way around, so it evens out before the sustain. And yeah, the way you set the parameter values is then just by addressing the FOSS instance, FOSS additive synth O dot set param value, and then you address the value we discussed earlier, which is decay 0 to decay 7, and then you give it a value. Then there's the sustain values. We keep them at the same level because the thing with the overall values we already did in the mixer. And for the release, we again do the same thing. So, okay, so the next thing I want to talk about, and that's a really, really cool concept, is having macro knobs. And what that does is you want to set the whole tempo of the harmonic oscillator at once, but you don't have a slider or knob to set each of the volumes, each of the 8 volumes individually then. So instead what you could do is to map those onto a single knob that goes from 0 to 127, and then, for example, make harmonic 1 loud in the beginning and soft or off in the end, but harmonic 2 do the inverse, be soft in the beginning and loud in the end. And harmonic 3 starting soft, then going loud, then going soft again. And then more variations of that, as you can see in the graphic here. The higher you go in this graph. And what happens there is that you get different combinations of timbres as you move along the knob. And is of to and so about the VMAX, I'll tell you. And we the meet call we're here we're seeing so stored node -1 means the node is off, so we're looking for the first instance in the array of 4 nodes that is -1. Then we're setting that array to setting that to the node, so we know, okay, well, node 1 is C0, and then we're assigning 1 voice to each of those numbers in the array, basically. So voice 0, you can read it as voice 0 has synth 0 and synth 4 assigned. Voice 1 has synth 1 and synth 5 assigned, and so on. And so this is basically polyphony code. And again, here you do that on my node off. You just switch those off again. If you find that the node off is the same as one of the nodes that's already in the array, then you switch it off and set it to 0. And then the most interesting part here probably is the my control change. It goes through the cases CC1, CC2, CC3, CC4, and so on as the on the and you set something to be right out of function, for example, the volume on the and then there's also in this just going to the set marble, catch the value and put it in the function. And so this is the code in Arduino. We need then to flash the code onto the TNZ. We need to connect the TNZ with a USB cable. Be sure to make it with a data cable. We need to connect the TNZ 4.0, and we set it to 816, which is a little overclock already, but runs really smoothly and doesn't get hot. We need USB type serial plus MIDI, and then we use the arrow to compile and upload. Let me show that real quick here. You just go here, and then you have either compile or upload. You hit the compile, it goes through a whole deal and starts compiling that, and then you can upload it to your Teensy, which we've already done, of course. So what is happening then is then you can combine the whole thing with modular.
Yeah, so I think our time is almost up, but we have a little patch which we would play real quick for a minute or so, right?
Yeah.
Yeah, so this is again the like try sound. And now I will patch it in some modules for basically effects.
Yeah, so what we're hearing now is running that into an amp, and then we use mutable instrument streams as a VCA. We use this not rocket science wobbler to make the nice wobbly sounds. And we use the Plinky, which is great DIY project, to add the cool reverb. And so that's it from us. Maybe we have some time for questions, but if we don't, then let us know.
No, sure, we have time for questions. And thank you very much, Enrique and Roland, for this very nice and very close to what we would have done if we were not in this special configuration that is a hands-on workshop. And so with all the camera, etc., I think we have all the information to redo that by ourselves. That was really, really nice. So we have time for questions. Do we have questions on the chat, or if you want to speak, please unmute your mic and speak and ask your question directly.
Let's see.
Okay, then I will start with one question about this set volume macro. How this, I think it's, as you explain, as soon as you are using real hardware, you run out of knobs very quickly. And so this is a way to control multiple parameters with just one knob. How the idea came from, and how effective is it? How easy is it to use?
The thing is, actually, a lot of modules in Eurorack do that.
Okay.
A lot of the DSP-based modules, especially, of course, because you always end up with code that has a lot of parameters you can set, and you just need to choose a user interface in the end that produces a nice result. And there's already I think there's already a choice in there, very much like what Max said in his talk, that well, you're building an instrument and it will be tilted towards a certain use. So, for example, here we thought, okay, you want to control the volume of the fundamental, because that's really a part of how weighty the sound is. But then you want to control the timbre maybe as a whole. For example, on a hardware knob, depending on the resolution, you would have much more resolution. For example, 4096 steps, and then you could fine tune that a lot more. But the overall idea that you group together parameters is really nice, because it also lets you play the instrument in a different way. There's some great examples of grouping attack and decay, or attack and release together on macro knobs as well. And you just start to set the envelopes differently as you would an ADSR envelope. So if we introduce 2 more parameters here, we have to, of course, give up 2 knobs of the ADSR, for example, and then you would just think of a nice way to still be able to use the parameters in a good way. Does that somehow answer the question?
Sure. No, that's really nice. There are other ways to control multiple parameters. For example, I don't know if Thierry, are you still here? Thierry Caron? Okay. We did a software with Thierry many years ago, where which was inspired itself by a software developed at gllm, and the idea is that you represent all your slider or knob on a 2D surface, and the value of the knob is the distance between, so you place all the knobs on this 2D surface, and the value of the knob is the distance between the place of the knob and the center of a cross that represents the center. And then, so you can move a slider close to the center or far from the center to change the value, but then you can move the center itself and change all the slider at the same time. So basically you do a two-dimension projection of a n-dimension space, and you can change the projection by moving the knobs, the sliders, but you can explore the projection by moving the center itself. So that's something that can be done with a joystick, for example. So that's a really interesting questions, I guess.
Yeah, that sounds great, and that's I think something that can be explored nicely in Rec, just because there are a lot of so for example, if you would imagine the knobs as CV inputs, which we didn't have the time to show like the circuitry behind it. If we wanted to show the circuitry behind building a whole module, then it would probably be like 10 of those workshops.
Sure.
Yeah.
But there are then, of course, modules that just do user interface. So there are modules that do joystick. So if you basically this matrix or XY axis projection that you talked about, that you could potentially do by hooking up a joystick module and plugging in
a CV input.
In a CV input, and
or
then
multiple CV inputs.
Then you would possibly get that plus the macro knobs. So so it I think it's really nice in Eurorack or in modular. You can sort of choose your control paradigm separately from the module itself.
I have a question on the cost of all the stuff that we can see here, and in particular the module made with the Teensy. How many euros do you have to spend for that?
So I think the Teensy itself is like $20, maybe.
Yeah.
Around 20. The audio shield, I think also like $20. Yeah, then pin headers, that's like penny stuff, you call it, I think. This we saw the connector to Eurorack, we soldered ourselves.
Yeah, so these are not available at Mutable Instruments, but they're open source. You can either order them yourself, the PCBs, and then you need to solder in pin headers and the jacks. But you can also buy them pre-made. I think Pusherman Productions has them, and they're, I think, 6 boards are €9 or something.
Yeah. So yeah, in total, I think like 55 euro.
Yeah, something around that. There's also, of course, other alternatives to the Teensy. For example, this is the Daisy board, and that's geared a little more towards, or that's geared completely towards audio development.
Yeah.
And we'll have Andrew Eikenberry talk about that, I think, in the last talk today.
Yes.
And it's a really, really great platform as well. So that would combine basically an audio shield and a microprocessor. And so, what was that? It was like $25 or something. So that's really great.
Yeah, but it has the audio codecs on it, so no need for a external
you don't need
codec.
An external board for the audio.
Yeah.
So, do we have any question from the audience? No.
I see a lot of chat about cool stuff we need to check out. Thank you, everybody, for that. So that's really cool. We're going to have to look through that as well.
So last question, because unfortunately, sometime at least from my point of listening, the audio was not always perfect, and so probably it's not going to be perfect on the YouTube stream. But I guess you did a registration of your own of the presentation that will be available somewhere.
Yes, we did that too. We tried to stream the whole thing in parallel on YouTube, so it's going to be on our YouTube channel.
Okay.
If everything, if all fails, we will probably just re-record it.
Yes.
I mean that would be another option.
Yeah, I'm sorry. The technical condition obviously is what it is, and especially for the audio, when you are just making a presentation with PowerPoint and voice, it's okay. But here we are in a more demanding situation, and it's far from perfect, unfortunately. But this was so packed of very useful information, so I think that that was really very interesting. So thank you.
Thank you for having us.
Yeah.
And so now we are going to move to the next talk, which is Romain Michon. So Romain is a full-time researcher at gllm. Previously, it was at Karma at Stanford. It's still at Stanford, but not presently with the lockdown. He is involved in the development of Faust since 2008, and it's now part of the core Faust development team here at gllm. And beside that, Romain's research interest involved embedded system for real-time audio processing, human-computer interaction, new interfaces for musical expression, and physical modeling of musical instruments. And in this talk, he is going to present how to build and play and program the gramophone. So, Romain, it's your turn. And maybe we will have a surprise after your talk, right?
Absolutely. It's easy to do all here. Yes, because this is asking before lunch. Because I'm deep down in the company right now. I'm show you after this presentation to control this, which is called so about that. Presentation is recorded.
I don't know, Romain, sorry, Romain, the sound is completely haché. So what can we do for that?
Maybe because training, people say it's for them.
Sound is bad, yes, yes. Sound is fine, good for me as well. Okay, so it depends.
I trim from two here, so once the video starts, it will be okay. Well,
okay, go on, Romain. For some people it's okay, and not for me, but it's not a problem.
Hi everyone, my name is Romain Michon and I'm a researcher at GRAM. During this 1-hour workshop, I will teach you how to build your own gramophone. That is the gramophone. And I will show you how to use it to make your own musical instruments. Now, before we get our hands dirty and actually start building our own gramophone, we need to answer a simple question. What is the gramophone? The gramophone is a mobile standalone musical instrument programmable with Faust. Sound is produced by a speaker and it is completely battery powered. The battery can last about 24 hours while it's on. It hosts various sensors that can be used to control the generated sound. You will find motion sensors, such as an accelerometer and a gyroscope, multiple rotary potentiometers and light sensors, which is a photoresistor, basically a microphone and a button. Yes, a button. They can all be mapped to sound synthesis parameters, as you just saw, directly from the Faust code. And that's something that we'll see later in this presentation, how that works. Other elements of the gramophone allow you to turn it on and off, to cycle between different Faust programs, to plug headphones, or to wire it to a mixer. The gramophone can be charged using a micro USB cable, which you can see here. The same cable can be used to connect the gramophone to a computer to program it. Now, some of you might be wondering, why the heck would you want to make this thing? So the first question we will answer here is why the gramophone? The gramophone has been created as part of the Amstramgram project. Amstramgram is a STEAM project bringing together services and resources for the educational community. The main goal of Amstramgram is to make abstract scientific concepts more tangible and concrete through musical creation and computer programming. Scientific concepts are explored through the programming of the gramophone thanks to the Faust programming language. Students eventually work towards a musical project with their teacher. And over 160 gramophones have been built and are already touring in the middle schools of the Auvergne-Rhône-Alpes region in France. So that is why we're making the gramophones. Besides that, they're fun to play and they can be used to write electronic music pieces. Okay, so let's now get our hands dirty and learn how to make a gramophone from scratch. These instructions can also be found on the Amstramgram website at the URL below. We will assume in this tutorial that you know how to solder and that you have some experience with hardware in general. Let's first have a look at the components which are needed to build the gramophone. By the way, feel free to get back to this list whenever is appropriate. You can also find it on the Amstramgram website at the URL below. First, you will need to acquire the gramophone case. While it cannot be purchased directly, the STL files of the case can be downloaded on the Amstramgram website and then printed using a 3D printer. If you don't own a 3D printer, which is the case of most people, you can also have them printed online and shipped to you. There are many websites that provide this service. I won't mention all of them here since they vary from one country to another. You will need a LilyGo TTGo T audio board, which is the heart and the brain of the gramophone. It is based on an ESP32 microcontroller and it hosts motion sensors and an audio codec. You will need an IMA 3-watt speaker. Make sure you get exactly this speaker model, otherwise it won't fit on the gramophone. Or, by the way, you could just download the source files of the case of the gramophone and adapt it to anything you want. The gramophone is a completely open source project, so all the sources are available online on the Amstramgram website. You will need a 3.7 volts 2050 milliamps per hour battery. Make sure you get exactly this model, otherwise it won't fit in the gramophone. That's just like for the speaker. By the way, we're sorry if we're showing you the links to retailers in Europe, but at least you will be able to get the part reference this way. You will need a small battery connector. There should be one that comes with the LilyGo TTGo T audio. You will need a 3-position switch. This kind of switch should have 6 pins at its bottom. You will need a set of 2 10K rotary linear potentiometers with their corresponding knob. Of course, the color of the knob doesn't really matter here. You will need one large 22 by 7 millimeter washer. You will need one 18 by 6 millimeters washer. You will need 6 7 by 4 millimeters washers. You will need a rotary encoder with an integrated button, 6 10K resistors, 1 photoresistor, 4 YLF TF 2.5 by 10 PZ1 AB SPAC screws, 10 YLF TF 2 by 10 PZ1 AB SPAC screws, 1 250 by 25 by 1.4 millimeter strap, 1 25 millimeter strap buckle. Let's now have a look at the supplies you will need to build the gramophone. Feel free to get back to this list whenever is appropriate. You can also find it on the Amstramgram website at the URL below. You will need electrical tape, white, red, and black 22 AWG stranded wires, heat shrink sets, solder. You will need 10 wires ribbon cable, Here I'm holding two of them next to each other's. One female IDC-20 plug. Okay, now let's have a look at the tools needed to build the gramophone. You will need a small plier. You will need a small wire cutter, a medium-sized plier, 1 8 and 1 10 millimeter wrench, one small Phillips screwdriver, one pair of tweezers, one stripper, one dentist tool, one heat gun, one multimeter, one soldering iron. This time we're ready to build the gramophone, so let's get our hands dirty. The first thing we need to do is to prepare the components before we install them in the gramophone. The first one we will take care of is the ribbon cable and the female IDC-20 plug. Cut two sections of about 12 centimeters of the ribbon cable. You can use regular scissors for that. Then put the two cables next to each other and slide them into the IDC plug. Once they are perfectly aligned, you need to force press the plug. There are special tools for that, and I don't have access to them right now, so I just used a clamp to do this. What's important is that the amount of pressure you apply on the plug is well spread on its surface, so using regular pliers is not a good option here. After you're done with this, you must separate all the individual wires and cut the ones that we won't be using as shown on the picture here. Feel free to pause the video at this point to look at this picture in more details. The next component we need to prepare are the two rotary potentiometers. They usually come with a small strip that needs to be broken using a plier. Just grab it with a plier and pull it. You'll have to do that on both potentiometers. Next, you shall solder the 10K resistor on the left and center pins of the potentiometer as shown on the picture here. We recommend you to pre-solder the pins to facilitate this operation. Make sure you bend the pins 90 degrees before you do that. In fact, you can see on the picture here that pins are bent. That's a very important step. You should cut the legs of the resistors to keep things clean. Put a heat shrink on the resistor. You should, of course, cut it to the right size. Then shrink it using the heat gun. Let's now prepare the encoder. The encoder should have pins on two sides, one with 2 pins and one with 3. Solder two 10K resistors to the side with 3 pins as shown on the picture. There should be one resistor on the left and right pins. The center pin should not be used for now. As for the potentiometers, pre-soldering the pins should make this operation easier. Now solder the two resistors together as shown on the picture. You should cut the legs of the resistor to keep things as clean as possible. On the back side of the encoder, solder a wire between the center pin near the resistor and the left pin on the other side. Now that the encoder is ready, solder a 10K resistor to one of the pins of the photoresistor. This type of component doesn't have polarity, so you can pick up any pin you want to do this. You can protect and insulate the pins of the photoresistor using heat shrinks as shown on the picture. This will prevent potential shorts in the gramophone. Solder a 10K resistor to the button. As the photoresistor, the button doesn't have a polarity, so any of the pins can be used for that. We can now prepare the speaker. First, cut 2 wires, one black and one white of about 14 centimeters each, and strip them on both ends. Make sure that you remove a very small section of the insulant on one side because the solder points will have to be very small on that end. We also recommend you to pre-solder the wires at this point. Now solder the black wire to the negative pin of the speaker and the white wire to the positive pin. Make sure that you use the side with the long strip on the speaker. The small solder points on the other side will be carried out later. Let's now prepare the battery. Be careful when manipulating the wires of the battery to not create a short. Lithium batteries can be slightly dangerous in that regard, so let's be careful here. Cut an 8 centimeters long red wire and soldering to the red wire on the battery to extend it. Then make sure to cover the solder joint with a heat shrink. Then solder the battery plug only to the black wire of the battery as shown on the picture. Insulate the solder joint as well as in the previous step. Finally, insulate the yellow wire that we won't be using for this project at all. Okay, we're now ready to prepare the 3-ways switch. Pre-solder the 2 leftmost pins of the top row and the 2 rightmost pins of the bottom row as shown on the picture. Now that all the components are ready, we can start assembling the gramophone. First, mount the first potentiometer as shown on the picture. It should be placed between the square hole and the large circular hole. The pins should be oriented towards the larger end of the case. Make sure it is fastened properly using the 10mm wrench. You can then mount the second potentiometer on the case. Look at the picture to figure out its location. The pins should also be oriented towards the larger end of the case. Make sure it is fastened properly using the 10mm wrench. Let's now mount the encoder. Note that the side with the resistors should be oriented towards the larger end of the gramophone. Make sure it is fastened properly using the 10mm wrench. Again, we can now mount the button on the gramophone case. The orientation of the pins doesn't really matter. In order to mount the switch on the gramophone, we first need to place the 6mm washer on it. You can then place it in the gramophone as shown on the picture. Once you put it through the corresponding hole, put the 7mm washer on the other side and then fasten it to the case with the bolt and the 8mm wrench. Put the photoresistor in the hole highlighted on the case with some kind of ring. You really can't miss it. It should just press fit in it, so you might have to push a bit on the photoresistor to go in its housing. Optionally, you can put some hot glue at the back of the photoresistor inside the gramophone to hold it in place. Now that most of the components are mounted on the case, we can start wiring them. Cut a small section of black stranded wire, strip it and pre-solder it, and then solder it as shown on the picture to the bottom right pin of the switch and to the left pin of the potentiometer right next to it. Do the same by connecting the left pin of the same potentiometer as in the previous step to the center pin of the encoder on the side with the resistors. Continue this chain by connecting the same pin on the encoder as in the previous step to the 10K resistor soldered to the photoresistor. Connect this last point to the left pin of the neighboring potentiometer as shown on the picture. We can now end this chain by connecting the last pin of the previous step to the 10K resistor soldered to the button. As you probably understood it, this wire is for the ground, so let's now bring power to the components using the stranded red wire. Connect the rightmost pin of the potentiometer right next to the encoder to the resistors of the encoder itself. Continue the chain by connecting the resistors of the encoder to the left pin of the photoresistor, which is basically not the one with the 10K resistor soldered to it. It's the other one. Continue the chain by connecting the photoresistor to the rightmost pin of the neighboring potentiometer. Finally, and this chain by connecting the potentiometer from the last step to the pin of the button without a resistor soldered to it. We're now ready to solder the ribbon cable to the gramophone. It will be used to connect the various components of the gramophone to the LilyGo TTGo T-Audio board. Solder the leftmost orange wire to the right pin of the potentiometer next to the encoder. This is basically the ground. Then solder the yellow wire to the left pin of the same potentiometer. This is power. After that, solder the green wire to the center pin of the potentiometer. The next wire on the ribbon cable is the violet one. You should solder it to the right pin of the photoresistor, which is basically the one with the 10K resistor soldered on it. You want to solder the violet wire to the pin itself, not the resistor, of course. The next wire on the ribbon cable is gray. Solder it to the center bottom pin on the switch, right next to the black wire. Then comes the red wire, which should be connected to the center pin of the potentiometer next to the button. The following orange wire should be soldered to the right pin of the encoder on the 10K resistor side. Here is a close view of the encoder so that you don't make a mistake. The following gray wire should connect to the encoder as well, but on the other side than the previous wire. It should be soldered to the pin without another wire soldered to it. The next wire is white, and it should be soldered to the leftmost pin of the encoder on the side with the 10K resistor. Finally, the black wire should be soldered to the pin of the button with a resistor on it, as shown on the picture. We now need to connect the battery to the system. Solder the two red wires coming from the battery to the two remaining pre-soldered pins of the switch. The speaker can now be mounted on the front face of the case using the 4 YLF TF 2.5 by 10 PZ1 AB SPAC screws with the small washers. There is no specific orientation for the speaker. Just put it the way you want. We also recommend you to cover the speaker driver with electrical tape to prevent potential shorts in the system. That's an important step. Actually, don't miss it. Make sure that the black and white wires of the speaker come out on the other side of the gramophone, along with the ribbon cable connector and the battery. On the LilyGo TTGo T-Audio, cut the two leftmost and the two rightmost pins of the male IDC connector as shown on the picture. You can use a small wire cutter for that. Now spot the future position of the board inside the case. The two remaining circular holes on the case should be for the microphone on the board and the jack audio output. Connect the battery to the board as shown on the picture. The battery will go behind the board, so you should take that into account. Connect the female IDC connector of the ribbon cable to the board as shown on the picture. The orientation of the connector matters, of course. Put the board inside the case and fasten it using two of the YLF TF 2x10 PZ1 AB SPAC screws. Make sure you put small washers between the screws and the board as shown on the picture. The battery wires should come out as well as the speaker wires. Solder the two speaker wires to the board as shown on the picture. The black wire should be connected to the negative pin and the white wire to the positive pin. Put the battery in the case on top of the board and put a thin layer of foam on it so that it is holding in place when we close the case. We can now prepare the strap. Attach the buckle to it by sewing the strap on itself. You could also staple it if you don't know how to sew. Burn the ends of the strap to prevent it from shredding. Install the strap in the back of the case as shown on the picture here. Buckle the strap up and the back of the case should be ready to be mounted on the gramophone. Close the box with the small screws. Mount the speaker grid on the gramophone and fasten it using the remaining small screws. You should respect the orientation on the picture. Finally, yes, finally, put the knobs on the potentiometers and the encoder. Your gramophone is now ready for showtime. Now that you have a gramophone, you probably want to learn how to use it. Since we don't have a lot of time left in this presentation, we just want to give you an overview of how the gramophone works in practice. Okay, so the first thing we want to do in order to be able to use the gramophone is to write a Faust program. And the program we're going to write here is going to be very, very simple. It's just to demonstrate the various features of the gramophone. So let's do it. So the first thing I'm going to do is I'm going to use the sawtooth wave oscillator because we love it. And as any sawtooth wave oscillator, because it's an oscillator, it needs a frequency. And I'm going to declare the frequency of the oscillator in a variable here, and I'm going to call it freq. And freq is going to be controlled by a slider in the generated user interface here in the Faust Web ID. By the way, guys, we're using the Faust Web ID here, which you can find at faustide.gram.fr. It's free, it's great, and you can use it to program the gramophone. Okay, so we were going to use the slider to control the frequency. And the first parameter of the slider is the name of the slider, and I'm going to call it freq, just like the variable to which it is assigned. The default value is going to be 500. The minimum is going to be 50. The maximum is going to be 1000. And we're going to use a precise step of 0.01. Okay. So now we have a sawtooth wave oscillator, and its frequency is controlled by a horizontal slider in the generated interface in the Faust Web ID, which we're not going to use right now because what we want to do is to control the gramophone. Okay. So the next thing I want to do is to be able to turn it on and off. And to do this, I'm going to create a gate variable to which I'm going to assign a button. And the name of this button in the interface is going to be gate. Okay. And all I'm going to do here is to multiply the sawtooth oscillator to gate. Sweet. So now I can turn it on and off, and I can control its frequency. But the sound that it's going to produce is probably going to be a little bit boring. So I'm going to use a cry baby effect, which is literally a wah pedal. Okay, and it has one parameter, and that parameter is wah. You can actually see that if you look at the documentation of the function just by hovering it. And you can see that the wah parameter is the pedal angle from 0 to 1. So here I'm going to create a new variable, which is going to be controlled by a slider. And the name in the interface of the slider is going to be wah. And I'm going to say that the default value for it is 0.5. That's like the middle of the range. The minimum is going to be 0. The maximum is going to be 1. And we're going to have a precise step of 0.01 as for frequency. Great. Okay. So now I can control the timbre of the sound. I can control the pitch of the sound, and I can control the fact that it's on or off. So that's enough for what we want to achieve here. So now if I want to use this program on the gramophone, I still have to connect those user interface elements to the various sensors which are on the gramophone. The motion sensors, the accelerometer, the gyroscope, or the physical controllers, which are on the case of the instrument, like the potentiometer or the button here. Okay, so let's start with the button. The way we do this is by using metadata. And here, all I'm going to say is that switch 1, which corresponds to this guy on the gramophone, is going to be assigned to the gate parameter. So it's not a switch, it's a button. But you know, we're French, so we do make English mistakes once in a while, you know. And so even though we say switch, we do mean button here. This is not a switch. Well, it depends on how you use it, but it is a button. Okay. Then I want to be able to control the frequency parameter with the potentiometer of the gramophone. So this one, because this potentiometer here is always for the gain. It's always mapped to control the gain, so the volume of the gramophone while you play it. So you can access this one with the metadata, but in practice, you never really do this. So we want to use this potentiometer here. And the way we do this is by saying knob colon, and this is knob number 2 because knob number 1 for gain is here. Okay. And finally, I want to control the wah parameter using the accelerometer. And the accelerometer metadata in Faust is standard. That's not just for the gramophone, that's for everything that has an accelerometer, and it's ACC con. And then you need to configure it. The first value I'm going to put here is going to be 0. That's the axis of the accelerometer. And 0 is for X, 1 is for Y, and 2 is for Z. Then you can map a curve, and I'm going to use curve number 0. I'm not going to explain to you what it does here, but if you're interested, you can just look at the Faust documentation to know more about it. And then those are acceleration parameters, and I'm not going to explain them as well. You know, like if you really want to know what this does, just look at the Faust documentation. I think that's the best way to do this. Okay. So wah is going to be controlled by the x-axis of the accelerometer. The knob is going to control the frequency, and the button is going to control the fact that the gramophone is on or off. Sweet. So this is ready. All I have to do now is to go in the export function of the Faust Web IDE, click on platform, and then choose ESP32. And architecture, I'm going to use the gramophone flash. Then you just click on compile. And after some time, you should have a gramophone program that should just be produced and that you can download on your gramophone. And I'm going to show you how to do this in this next step. Okay, so after about 15 seconds, you should have a QR code that displays to your screen. And you are now able to download the gramophone program that was just generated by the export function of the Faust online compiler. So you just download it. After you downloaded it on your computer, you can use the Gramo loader, which is this little program here. It's free. You can find it on the Amsterdam website. And it's free to download. It works on the Mac, it works on Windows, it works on Linux. You have different versions. And all it does is that it creates some kind of bridge between the Faust Web IDE and the gramophone. Okay. So in order to do this, you just have to select. Okay, of course it's in French, you know, like, but you just have to get used to that kind of stuff, you know. Like eventually we're gonna make an English version, but there are so few things to know about this program because it's so simple that for now, French is gonna be the rule. Okay, so here I'm just gonna choose the file that was downloaded on my computer. It's binary.zip, and binary.zip landed on my computer in my downloads folder. And I'm just gonna select it and I'm gonna open it, and then the programming of the gramophone will start happening. This operation will take about 20 seconds. So I'm probably going to see you after that. And eventually, once it's done, you will get a message in the Gramo loader application that will tell you that the programming of the gramophone was successful operation. So let's wait for it. Okay, it just happened. So now we're actually ready to play with the gramophone. You just put it on your hand. By the way, I don't know if you saw that, but the strap is slightly lower on one side than the other. It points towards the ground, you know, so that's where you should put your hand. Don't hold it like this. You have to hold it like this, okay? And eventually, if things actually worked the way that was planned, if I press the button here, I should hear a sound. And it makes a sound, so we're actually happy. So audio is being triggered by the button. I can control the frequency with the knob here. Nice. And I can control the gain with the gain button that I just have over here. And I can control the wah parameter using the accelerometer. Nice. So that's pretty much everything you need to know about the gramophone. One feature that we didn't see yet, is the fact that you can switch between different Faust programs installed on the gramophone using the encoder here. I'm not going to show this feature for now because we don't really have time for it. Finally, one thing you need to know is about this little switch that you have here. This switch allows you to turn the gramophone on in battery mode. So if the switch is at the center position, it's a neutral position, the battery is not connected to the gramophone. So in that case, if you unplug the cable, you will lose sound. Because now the battery is not connected anymore to the gramophone. On the other hand, if you want to connect the battery to the gramophone, you have to go from central position. Once again, there are 3 positions, left, center, and right. At least from my perspective, it's probably different from yours. So here, if you push it towards the knob next to it, it goes in battery mode. And now you should be able to play the gramophone with the battery. Okay, and finally, the other position with the switch allows you to force the fact that the gramophone is being programmed, because sometimes it can be stuck. All these informations are better documented on the Amstramgram website, so I just recommend you to have a look at it. Okay, so one last thing to conclude this little tutorial. Once the connection is established between the Faust IDE and the grammar loader through binary.zip, you don't have to select it again afterwards. So it means that all you have to do if you make some changes to the Faust program here is to click on the export button. And just clicking on the export button will produce the gramophone program and will also install it on the gramophone connected to your computer. So you don't have to select the program once again. That's it, folks. If you have any questions, feel free to send them to me by email. I hope you enjoyed this presentation. Okay. There we go. Sorry, it's kind of a complex setup here. So yeah. Yeah, so I will take questions if you have any. I think I replied to most of the questions that were asked in the chat. But yeah, if you have some live questions, feel free to ask them.
Maybe I have 2 questions, Romain. What about the price of building a gramophone?
It's a good question. So if you just get the parts and if you have the case 3D printed somewhere else, so if you don't have a 3D printer,
like the total price is about 110, 120 euros or something like that. But if you have a 3D printer and you print the case at home, of course it will be even cheaper than that. You know, like, so it will be more like 80, 90. Maybe like, yeah, actually 70 or 80 euros or something like this. So yeah.
Can you also explain the difference between the the Faust ID in normal mode and the Faust ID in Amstramgram mode or gramophone mode?
Yeah, it's a good question. So basically, in Amstramgram mode, the ID is much simpler than in the regular mode. So many of the features are hidden, so that students who are like, once again, middle school students don't change parameters, which might completely screw up the setup of the Faust ID and don't have any sound coming out of their computer. So yeah, the whole idea is to prevent students from doing something stupid, basically. So yeah, it's the same, but with less features.
Are there any questions from the audience?
Yeah, I'm sorry if this was a little bit dry, but like, I mean, this was supposed to be a workshop where people actually make something, like, and of course, this is not something that you guys could have done in that case, or we could have better prepared things, and ask people to pre-order parts to build their own gramophone at home, like, but yeah, so at least we hope that this will be useful to people who actually want to make the gramophone later, but yeah, I'm sorry if like, all these technical details are not so interesting potentially, in that context, but that's what online workshops on hardware are, I guess. So yeah.
Okay. Are there any questions?
Is the gramophone more compatible with other ESP32 audio boards? Well, not really, because there's if you want to make a gramophone which has exactly the shape of the one that we have here, with the STL files that are provided on the Amstramgram websites, the form factor of the board is very important. And so only that specific board will properly fit in the gramophone. So of course, like, I mean, you could get another board, and because it's an ESP32, you can program ESP32 with Faust pretty easily. Like that part doesn't really change. But you could adapt the STL files of the gramophone case so that they fit with another board. But if you want to use another board, you'll have to change the files of the case of the gramophone, probably. So yeah. I saw there were other questions in the chat, but I don't see them here. Maybe Jan, you can moderate the questions in the chat. Okay, no, I can see them now. So
okay.
How are the TTGo built-in codecs WRT SNR? Is it advised to use other codecs for performance applications? Well, that is a good question. So the codec on the TTGo T audio board is the same as the one on the iPhone. So it's actually relatively good quality codec, and so the sound quality of that codec is actually pretty good, and there are a few weird things on the TTGo T audio board, especially the wiring of power on the codec in relation to Wi-Fi on the ESP32 board is not really done properly, and so there are some features of the board that you can't really activate if you still want to have audio running on the system. But if you just use it for basic applications, the audio codec is actually relatively good quality on the TTGO T audio board. So yeah. Okay, there are many questions. So okay, then could the gramophone be modified to accept audio inputs so it could work as a sound processing unit? That is also a good question. So there is a microphone on the gramophone, so that is an audio input, but I guess that doesn't really answer your question. So the TTGO T audio board, weirdly enough, doesn't have any line, like physical line inputs on it. However, the audio codec on the TTGO T audio board has a stereo line input on it. It's just that it's not wired at all. So if you're very good at soldering, and if you have very good eyes, and if you don't shake too much, you could potentially solder wires directly onto the codec of the TTGO T audio board to retrieve the audio inputs. I think that's the only way to do this. And it's probably hard to do. Well, I mean, it's not so hard, like from a technical standpoint, but like soldering on an audio codec by hand is pretty intense. But I've done it before, and it works, but it's hard. Okay, so there are more questions. Okay. Okay. There are comments, but I think that's all the questions that were in the chat, right? Or maybe I missed some more. Okay, cool.
Okay, so thank you very much, Romain. It was very detailed and very. I think that you can really rebuild the gramophone from this video. So it's going to be super useful, especially because we don't have we built some of them for our purposes, and we have more than 100 of them, but yeah, we don't have a unit to fabricate them. So
yeah, Thomas Hopman made very good comments about this actually in the chat. You know, and the fact that we don't make PCBs for the gramophone yet. We actually made a very like primary version of the gramophone with a PCB, and it's true that in terms of putting it together, it really helps. But I think in our case, and the way it is used and provided to people in the framework of the Amsterdam project, it was kind of easier to do it the way we did it. But it's true that using PCB would definitely make things easier in terms of assembling the whole thing. So yeah, maybe a future version, but I feel like for now, and also from a pedagogical standpoint, which is also like something that I didn't really talk too much about in the video, but there are actually students who are going to make their own gramophone in some middle schools, you know, and the soldering aspect of things, you know, and wiring things and cutting wires was something that was actually really asked by the teachers. So that's also one of the reasons why we did it like this. But yeah.
I don't know if you saw it, but there is a question by Peter Kim about the availability of all this information.
So whether this video was the first documentation or
I may have missed a GitHub repo for the gramophone. Well, everything is on the Amstromgram Git repository, which I posted earlier in the chat. So if you scroll up in the chat, okay, and they are, but they are deleted in the end. So, okay, let me. The problem is that I have a complicated. Yeah, there we go. Amstromgram making. Okay, so that's yeah. You found the source. You found the source of what's on the Amstromgram website, and it's a markdown file. So in terms of making the gramophone, everything is here for now. You know, because we'll just assume that the video are the instructions. So yeah.
Okay, so thank you again, Romain. This afternoon we will have also 3 talks. Don't miss the first one, don't miss the second one, and don't miss the third one. The first one will be by Xiong Ren, and Xiong is the guy that did the Faust IDE during its internship here at Gram. So it's a very bright programmer, and he's doing a completely new project, which is Faust, how to say that, a graphical editor for Faust. And so it's probably a solution to learn Faust much more easily than with the textual language itself. It's a kind of Max, but directly in Faust. And then we will have a talk by Stefan Letz, and presenting how you can use Faust to make VCV rack modules directly from Faust, and using also the Faust IDE. And finally, we will have a talk by Andrew Ekenberry, which is the author of or the designer of the DAISY board, which is a super interesting board, especially because it has all the audio already wired on the board. So don't miss this afternoon, and so we will have a lunch break. And I don't know, Romain, if the invitation of coming to your house for having a truffade is still
Okay, so the thing is, we, you know, like usually in France, before you eat the haricot, you need to drink the aperitif. And the issue is that haricot is something that you have to eat on the spot, because it has to have like the perfect texture for it. But however, I'm just gonna give you the recipe before I actually make it. You know, like so. But we need to take the aperitif first. So that's why. But basically, you need nice mashed potatoes in which you will add a lot of cream. Because in the mountains in France, we like cream a lot. So we put cream in everything. Okay, and because that's not really just fat enough like this, once it's hot and warm, then you can add this thing, which is a very specific kind of cheese that you find in the mountain in France. It's called tome fraîche, and it's very soft. And so you add the cheese to the mashed potatoes, and then eventually with some garlic, you mix it all together, and eventually when you mix it, it will become this sort of paste, and it's going to be very tough to do. Like you need to have like very strong arms, otherwise it doesn't work. And like sometimes you even break the spoon because it gets so hard, you know, and eventually you eat that with the prosciuttos and salami. So we'll probably eat that in about an hour here once the aperitif is done. But yeah, if you want to know the recipe, I can send it to you. I can send it to you directly in the chat or by email. You know, it's very easy to make. The hard thing is to find the soft cheese, which you can only find here basically. So yeah.
Anyway, bon appétit, guys, and see you later this afternoon.
Okay, bye bye, guys. See you this afternoon. Don't miss the Aligo and the 2 p.m. talk. Bye.